Forests are essential ecosystems for life on Earth. They cover 30% of the surface of the Earth, from the tropics to the boreal regions, from the coast to the high mountains. Some of the biggest and longest living organisms on the planet live there. Trees, with some individuals that manage to survive for hundreds, even thousands of years. Forests serve as the habitat of an enormous variety of living beings, and they play an essential role in the cycling of water, carbon, oxygen, nutrients, and soil formation. Their peaceful and harmonious appearance hides intense battles for survival, with numerous and complex interactions among its members which are currently being deciphered. Owing to their large size and longevity, trees are exposed to many natural enemies. Throughout their lives, they undergo countless attacks from herbivores, mainly insects and vertebrates, as well as other harmful organisms such as bacteria and fungi, against which they must defend. Trees that are capable of overcoming such attacks and obtain the necessary resources, light, water and nutrients, will survive and successfully reproduce. To cope with the constant aggressions, plants have developed complex and varied defensive systems that prevent or delay their aggressors' advances or diminish their performance. Until recently, the reaction of trees when confronted with their enemies was seen as a simple and passive process. However, we now know that their defense mechanisms are much more active than previously imagined. Trees, just like other plants, are able to control their defenses according to the risk of attack and the existing environmental conditions. The effort they make to protect themselves is not constant. In the same way that the immune system of human beings responds to an infection, trees react to threats by producing more and new chemical and physical defenses. The synthesis of defensive substances is highly costly for plants, and for this reason, they usually produce defenses only when it is strictly necessary. In this way, they achieve a maximization of growth and reproduction when the risk involved is low. This strategy is especially relevant in trees which, owing to their longevity and size, must deal with countless dangerous situations. Researchers from the Spanish National Research Council, CSIC, at the Galician Biological Mission have observed that in pine trees, the content of resin, their main defensive substance, increases as much as fourfold when they are attacked by the large pine weevil, Hylobius abiatis. This weevil, of the Curculinidae family, eats the bark and the phloem of young pine trees, causing great losses in the forestry sector in the whole of Europe. Attacks from this insect induce or lead to morphological changes in the resin duct system, which protects pine trees in the medium and long term. Trees, like other plants, feel the damage caused by their enemies, identify the organisms causing the damage, and react accordingly. The damaged parts send out a message of danger using chemical signals to the rest of the tree and warn of the need to prepare and increase defenses. Upon receiving such a signal, plants may stop growing and devote their resources to producing chemical and physical barriers, accommodating their anatomy and physiology to the risk. But these responses are not always the same. They depend on other factors such as the enemy that is causing damage, the intensity of the damage, and environmental factors such as availability of light, water, and nutrients. Recent studies in this field show that one of the most characteristic defensive mechanisms is a change in the emission of aromatic compounds to the atmosphere. Many volatile organic compounds are constantly released by plants and, in particular, by trees. This release is perceived by us through the particular smell given off by a pine forest, a eucalyptus plantation, or a laurel forest. The alteration in the relative concentrations of these substances could be an effective system of internal communication for the tree. In this manner, it warns of the presence of an attack to parts that are far away from it, without having to resort to the slow transport of a chemical message through the vascular system. With these subtle variations in the emission of volatile substances, trees may attract other insects that are the natural predators and parasites of the herbivores, and also insectivorous birds which approach the tree in search of food. They thereby manage to indirectly reduce the pressure of their enemies, establishing a network of relations with other inhabitants of the forest which, as if a language were involved, interpret the messages issued by the trees. But do they use this particular code of volatile substances as a communication system between neighboring trees? If this is so, then plants that have not yet been attacked, upon receiving the warning messages in the volatile substances released, could get ready for a possible attack. Research in this field is now focused on resolving these and other uncertainties about the various forms of communication between different parts of the same tree, among different trees, between trees and insects, and even between trees and beneficial fungi. We now know that trees can perceive changes in the surrounding environment. They can detect the presence of damaging organisms, they can identify them, code them, activate their defenses, and change the concentration and composition of the volatile substances released. A new and complex world of interactions is now open, where there are many organisms involved in this language of forests. In the last decade, great scientific developments have shown the various responses and defensive methods of trees and the way they interact in their environment. What is seen by the naked eye as a world of apparently static harmony is in fact a constant battlefield, with enormous traffic of information between its combatants, in which a multitude of armies and alliances participate. The survival of our forests does not only depend on trees, but on the joint action of all their members, as even the contribution of the smallest organisms may be essential. Understanding the flow of information and who the members involved in this singular community are is an ambitious challenge for science, and, from the research point of view, we could say that we have entered the era of the communication of plants.